Hi, y'all. So I am going to talk about friction in this little mini lecture. And I hope that by the end of it, I will convince you that friction is fun. Okay, so we've got three different situations on the right-hand side of the screen here. We've got somebody pulling on a rope just a little bit, somebody pulling on a rope a fair amount, and then somebody pulling on a rope a lot so that we finally get the block to start moving. Um, Now, the first thing that kind of leaps to my eyes right there is that, well, if you look at it, that's kind of mislabeled, isn't it? That's a tension force that's acting on the box, not just a F force. I don't know what that is. At any rate, on to the point that I'm actually going to talk about on this slide is friction. Okay, when we've got two objects that are really kind of trying to slide across each other. What is the force that resists that motion? It's friction. You know this. I'm not telling you anything new. Well, when the two surfaces are trying to slide but have not yet started sliding, so they're not sliding, this is what we call static friction. And typically, if we think of static, we think of like static electricity or something like that. This is not what static means in this case. Static means staying still, so resting. So not moving actually is literally what static means there. So when we talk about static friction, we're talking about a situation where our two objects are not sliding against each other. Oh, my hands are getting hot. I wonder why that is. It's friction turning into heat. When we've got two surfaces sliding against each other, well, this is what we call kinetic friction. And we dealt with kinematics, which was the study of how things move. Well, kinetic sounds a lot like kinematic. Well, kinetic means moving. So when we talk about kinetic friction, we're talking about two objects sliding across each other. The specific friction that we have in these diagrams, we see that subscript S there. That's static friction, and specifically right here at the bottom where motion just starts. What happens? We pull a little bit, we pull a little bit harder, we pull a little bit harder, and as we continue to pull, that static friction force resists us more and more and more until finally it can't resist us anymore. It's hit its maximum value, and that's where motion starts. All right, so it'd be nice if we were able to calculate some of that. So let's take a look at what we have here. We've actually got a way to calculate static friction. At least a way to calculate our maximum static friction. So our maximum static friction is given by this equation right here. And if I'm going to write it out, and I'm going to be proper about it, I should really write it out as a small n there, not a capital N. Small n for, what's that small n? That's normal force. So thinking about what's going on here, well, our maximum static friction is equal to this mu times this normal force. What's mu? Mu is what's called the coefficient of static friction. So that's going to vary depending on what our two surfaces are. So I could rub my hands against each other. That's skin on skin. I could rub my hand against the cover of this book. Maybe that's skin on cardboard or something. I don't know what. You know, I could have tires sliding on asphalt, something like this, or concrete. That's got a slightly different coefficient of friction. The coefficient of friction depends on the two surfaces, and so we'll have to rely on either problems telling us what the coefficient of friction is, or looking that up in a set of tables. Now, my static friction is always going to be less than or equal to that maximum value. So I can calculate the maximum value with this handy little equation right there. Friction is, check it out, F mu n. Friction's fun. Looks like fun, right? So I can calculate it with this fun little equation there if I want to know the maximum value of static friction. But if I, maybe I'm not pulling that hard, then I can't use this equation. I would have to rely on some other method to calculate my static friction. All right, that's great. What about when we've got motion? So static friction is dealing with things that aren't sliding against each other, like my hands right now. But if I've got motion, now I've got kinetic friction, or maybe I've got my hand sliding across the book there. There we go. There's kinetic friction resisting my hand sliding across the book. Well, in this case, instead of having that less than or equal to that we had for static friction, we've got just an equal sign. And so kinetic friction is equal to the coefficient of kinetic friction times the normal force in there. And again, friction's still fun. Yeah, corny, right? So friction's fun. There we go. And that's our equation for how we calculate friction if we've got normal force. If we know, for instance, how hard I'm pressing on this textbook, then we would know the normal force that the textbook is pushing back with against my hand, and then we would be able to calculate that kinetic friction value as my hand slides across if we knew the coefficient of kinetic friction between the skin of my hand and this textbook. All right. Here are some values for coefficients of friction. We've got the static and we've got the kinetic right there. Okay, so what maybe are we interested in? Well, there's some rubber on dry concrete and wet concrete. Static friction is okay. That's a car stopping under control. Kinetic friction is a car that's more or less skidding across the road. That's not so hot. So that's not so good. We've got others here, and then of course we can look up whole long lists of tables of these on the internet. All right, so let's check out maybe a problem here. It says I press a 3.5 kilogram textbook between my hands so that the spine of the textbook is vertical. Okay, so here's a demonstration of that. There we go. Okay, so something like this. It says, what is the force keeping the textbook from sliding down? Duh. We just talked about it, right? It's static friction. Yeah, it's specifically static friction. Why static? Because the textbook is not sliding. Now it is. Now it's kinetic friction. Oh, sorry. Then it was kinetic friction. Right now, when it's not sliding, it's static friction. All right. Well, how many static friction forces are there? What do you guys think? Form an opinion here. How many static friction forces are there? Well, actually, there's two. There's a static friction force between this hand and the book, and there's a static friction force between this hand and the book. Okay. And what's the direction of those static friction forces? Well, let's see. In order to figure that out, we can maybe start to draw a free body diagram. We know that we've got the weight earth on book downwards. And then we know, let's see, what else? This hand, my right hand, hopefully that's my right hand for you guys. My right hand is pushing on the textbook. So I've got a normal force of my right hand on book. And then I've got a normal force of my left hand on the book going this way. Okay, so if I think about that, then let's see. Normal of right hand on book. And what would the size of the normal force on the left hand on book be? Well, it better be the exact same. Otherwise, the book's going to be going that way, right? So those forces have to be balanced out. Yeah, it's kind of odd that the right hand is the arrow is on the left side, but I'm pushing to that side with my right hand. So that's the way that works. All right. So what else do I have? I've got, let's see, obviously my static friction force. I'm also getting distracted by email, if you couldn't tell. How many static friction forces? Well, two. Two hands, two upward static friction forces. All right, and both of those guys are going to be directed that way. Combined together, they must sum to whatever the weight is. So they've got to counteract the weight. So they're going to be about half the size, or actually exactly half the size of the weight force. And so this is a friction of left hand on book and friction of right hand on book. I got phones going off and everything else. It's awesome. Okay, so there's my free body diagram. Let's see what's next. If the coefficient of static friction between my hands and the textbook is 0.8, how hard must I push with each hand to keep the textbook from sliding? All right. So my coefficient of static friction was 0.8. And my free body diagram, if I'd planned ahead, maybe a little better, looks like this. I got friction, friction. I've got a normal force. Let's see, let's make sure that we're actually, whoops, wrong thing. Let's make sure that I'm actually, well, what happened there? Make sure that I'm actually using the correct notation. Normal force, small n, normal force. And then we've got a weight force downwards. There we go. All right. There we go. Let's see. I've drawn my free body diagram. What's next? Labeling my x and y directions. All right. All of my vectors either point in the x direction or point in the y direction. So that's all set. I don't have to break any vectors down into components. So the next thing would be Newton's second law. And specifically, I'm really interested in the y direction. So let's write Newton's second law in the y direction. The sum of the forces is equal to mass times acceleration in the y direction. Well, the textbook's not accelerating at all in the y direction. It's holding still when I hold it like this, right? It's not moving. The acceleration is 0. So my acceleration in the y direction is 0. There we go. Boop. Acceleration in the y direction is 0. And then what do I do on the left-hand side of Newton's second law? Well, I fill in exactly what my free body diagram tells me to. I've got two different friction forces, F plus F. What's this? And then I've got a weight force. Okay. All right. Incidentally, or maybe not incidentally, but we have to think about the relative sizes of those friction forces. Well, let's see. How do the sizes of the normal forces that my hands are exerting on the textbook compare to each other? As I discussed in the last slide, they've got to be the same. Those normal forces have to be the exact same size. If not, the textbook would be moving, and it's not moving. It's staying still. So if the normal forces are the same size, and what do we know? We know that friction is what? Friction is fun. Friction is fun. There we go. If the normal forces are the same size, and I've got skin on textbook cover and skin on textbook cover, the mu's are the same size, then my friction forces from each hand have to be the same size as well. So what's this tell me? This tells me that these guys are both the same size. I've got F plus F gives me 2F. 2F must be equal to W. If I move that over to the other side, friction is equal to, divide both sides by 2, W divided by 2. And what's W? W is mg divided by 2. What's m? M is 3.5 kilograms. G is 9.8 meters per second squared. Divided by 2. Punch this into a calculator and it'll give me the result 17.15 newtons. All right, great. That's my value for friction. Well, I'll take my fun equation. There's fun. And I know that if I rearrange this guy, divide both sides by mu, my normal force is equal to friction over mu. This is 17.15 newtons divided by my value for my coefficient of static friction, 0.8. And I get out that, well, the normal force that I have to push with is 21 newtons. So I have to exert 21 newtons with my right hand, and I have to exert 21 newtons with my left hand in order to keep this textbook in place, given the kind of made up numbers that I gave us for the mass of the textbook and the coefficient of friction. All right, guys, that's it. I know this was kind of long, but I hope that you got a lot out of it, and we will talk more about friction in lecture. Absolutely.